without further ado, I'm going to introduce our first speaker. He is a long-term friend of the Embedded Vision Alliance and a very popular speaker at many past summits. I'm sure this is going to be an excellent talk as well. Yury Gorbachev is a principal engineer and lead architect for the OpenVINO Toolkit at Intel. And how I got to first to know Yury, he was previously a principal engineer at ITSEs, which was acquired by Intel, responsible for embedded platforms and automotive algorithm deployments. And his talk is going to demonstrate how the OpenVINO Toolkit from Intel makes it easy to move deep learning algorithms from research to deployment. Yury.
Thank you. All right, thank you for introduction. As it did mention, we will be talking a little bit about how do we get the best applications with the OpenVINO. We will not talk about why we named it OpenVINO. So if you expected this to happen, that won't, right? So, but other things that were promised will happen. So first of all, OpenVINO was introduced exactly a year ago on the same conference. We made an announcement that OpenVINO Toolkit will be available to the customers. Will be broadly available because we've been developing this toolkit for a while, like for a few years before. It was like in a beta stage last year, exactly same time frame. We've been announcing the public availability, and now we're sort of celebrating first birthday, and it makes sense for us to do a little bit of a little bit of understanding what happened in last year. So what happened is actually we got quite a lot of customer base in different areas, covering retail, security and surveillance, and other areas that Intel is working with. And we get a pretty good feedback in terms of like accelerations that people are getting, in terms of network support, in terms of usability of the tool. And more importantly, moving on, we are not only positioning this toolkit as an end-user application library, but also not just a deployment library, but also as an underlying building block for a few frameworks that are used for execution of the inference, right? That's sort of in terms of where we are and technically. We are getting more and more mature. We are releasing more and more products. So, for example, Movidius NCS2 stick that was released middle of last year, by the fall last year, is supported by OpenVINO. We have a support for FPGA cards. We have a support for new processors and GPUs. And the trend is that actually we are planning to expand on the new hardware and new accelerators that Intel is producing. We do quite a lot of major releases. To tell the truth, from the development standpoint, we think, how good is this that we have major releases every quarter? That never happened. We have releases even before those releases and things like that. So we do quite a lot of updates. We do quite a lot of functional changes. So I wanted to talk a little bit about what we have done, right? And more importantly, we made this toolkit available as open source. Since it is running on CPU, and CPUs are widely spread, and you can do development on CPUs, you can also go and do the contributions into the open source if you feel that some things are missing, or if you feel that you can improve certain things. So why OpenVINO in the first place, right? So Intel spent quite a lot of resources doing optimizations of the public frameworks, like for example, TensorFlow, Caffe, AMXNet, all of those things were optimized specifically for CPU, specifically for like a Xeon data center CPUs. But at the same time, the frameworks are always oriented on a little bit wider scope than just inference. So for example, you can train the networks, but also at the same time, you can do the inference through the frameworks. So if you just concentrate on the inference, which OpenVINO Toolkit does, then you can get additional acceleration. So here we have some numbers for the Core i7 CPUs, which are mostly widespread, and basically the numbers are in two categories. So the performance that you get when you're doing the inference of the deep learning networks, as well as memory footprint, because memory footprint is extremely important for certain use cases. So for the TensorFlow, we get about 2 times acceleration comparing to the most optimized version of the TensorFlow that you can find, as well as we have 5 times less memory. And the same thing we can say for MXNet and Caffe. It's just different percentage, but when it comes to the memory, we do quite a lot of work on reducing the runtime footprint, as well as the memory used for intermediate activations and things like that. So just performance and footprint is the reason to switch for OpenVINO in terms of running on CPU. But at the same time, we also expose exactly the same interface, exactly the same API that we have for CPU to other platforms that Intel provides. We have support for GPU, we have a support for NVIDIA's VPU. As I did mention, we have a support for NCS2 stick, for example, and other accelerators that are based on VPU, as well as we have support for FPGA based accelerators. So all of those things are available through the same API that we expose to CPU. At the same time, we're trying to make it as easy as possible for applications to be written in a portable way. So we do different API changes that allow, for example, to do device enumeration, device aliasing, so that you can move applications as much as possible between different deployments. Depending on which hardware you have available in certain deployments, you can run differently, or you can run on different targets. Moreover, one of the biggest things that we've been trying to implement, and that was one of the design constraints that we had, was actually that results of the execution that we have in OpenVINO must match with the original framework. So if you go with the framework and import and run, then you get consistent execution. And then we have heterogeneous execution, which is execution on multiple targets as well. So architecturally, OpenVINO is pretty simple to use. If you have original network in all of those formats that are listed here, like TensorFlow, Caffe, MXNet, you can just import this network through the model optimizer tool. Some things will be happening on the background, some layers will be removed, some optimizations will be done with the layer fusion and so forth. And you will get the network that will be hardware independent, but will be significantly faster. The network will be in the intermediate representation format that's framework independent, and then you can just start using Inference Engine API to run on all those hardware families that we have. So you don't need to have a framework anymore, but we guarantee that results of the execution of the network that you do through the Inference Engine API will match the results of the original framework. So if you had an application that was actually using framework, you can easily switch to our Inference Engine solution. So one thing that we have specifically introduced recently to accelerate the networks was built-in tools for int8 quantization. Int8 quantization is now being the most popular optimization technique. We have recently released a Cascade Lake Xeon family that contains technology called DL Boost, which is essentially optimizations for int8 execution. As well as you still have old-fashioned instructions for executing int8 on CPUs. So if you have a capability to run int8, that would be additional benefit that you will get on those platforms. So that's exactly what we are providing. If you take the IR that you imported through the model optimizer tool, and you run this through the analysis tool that uses some reference data set, you will get updated IR. So essentially, this is framework independent tool in a way. And then you can just continue using your regular code with updated IR, and then you will get the int8 model. The performance numbers that you would get would be like 40% on regular i7 core, and this is at least 40%. So that would mean, depending on the network, you can get significantly higher acceleration. As well as you can run more than 180%, as you can see on the Xeon, using the DL Boost technology that was recently released. We do have a release support for binary networks, so we can execute, as you can probably see on our booth, we have a partnership with company called XNOR AI. We are able to run the networks from XNOR AI. We have our own internal research where we have released networks with the binary layers. So you get additional acceleration through the binarization. If you have a need for custom networks, potentially you can work with XNOR AI and get the execution on Intel through OpenVINO. That would be truly supported, right? So we're also working on supporting importing networks that are quantized through the framework. So for example, if you're using TensorFlow fake quantization, you can import that, and you will get in-state quantization. You don't have to do analysis tool or anything like that, right? So when you run on CPU and GPU, one of the things that you get is that memory is very close to the execution. But if you run on the discrete accelerators, or like VPU-based accelerators, NCS2 stick, or like PCI form factor, or FPGA-based accelerators, then one of the problems you have, and this is actually the same thing for discrete GPUs, is that you need to transfer data and then do the execution. So paralleling of the data transfer with the inference actually gives you additional throughput. So we have a mechanism that allows you to do that through the OpenVINO. We call it synchronous API. So essentially, what you can do is that you can send multiple inference requests to the device for inference. And what happens is that the inference engine will automatically do the transfers in parallel with the execution. And you get like 65% more throughput in terms of like pure FPS on VPU-based accelerator, and you get 40% more throughput on FPGA-based accelerators. So by just using asynchronous API, by sending more and more requests, you get additional FPS out of your system. So moving on, there is a common concept that batching is accelerating the inference, right? So that's actually to some degree true, but it's not fully applicable to all the platforms. So on some platforms, you can realistically have significantly more acceleration by doing different techniques. So one of those techniques is actually the technique that we call throughput mode or parallel inference streams. So what you can do is that instead of sending one inference request after another and receiving results, you can just send multiple requests, and system will, first of all, as I did mention on the previous slide, system will do transfers in parallel with the execution, but also for the cases when it is applicable, system will do parallel inferences. So like in case of Xeon, in this particular case, this is 56-core Xeon, which is like typically data center installation. In case of Xeon, if you run single inference, you are not very efficient. So by batching, you get like 56% acceleration, which is probably okay. But if you run just multiple parallel streams, you get 83% more, at least 83% more. So that means that instead of collecting frames into batches and things like that, you can actually do independent streams which are not related to each other, and you get significantly higher optimization comparing to batch. So you don't bother about collecting stuff into batch, but you get faster execution and significantly higher throughput. Then one of the things that I specifically want to look at is the image processing pipeline. So if we look here, this is the typical, I would say to some degree, typical security surveillance scenario. When you have a decode, when you're obtaining frames from the camera, doing decode, then you have to do layout transformation because most of the decodes are actually NV12 or similar format. And typically, the network format that you get or you train on is actually RGB or BGR or something like that. So first of all, you need to do the format conversion. Then you need to do resize to the frames to the frame size that is accepted by the network. Then only then you do the actual inference, which is blue box there. You do the deep learning inference, and you're getting like bounding boxes for the objects you want to detect, like vehicles and so forth. And then you have a second step typically, because you don't just want to detect them, you want to do something with this. So you have to crop the bounding boxes from the frame, again resize them to a second network and do the inference. So as you can see, out of the whole pipeline, the actual deep learning inference taking just 2 boxes out of 7 here, right? So combining all of this, is actually combining all of them efficiently is a very challenging task. So most of the people that we have seen using like either OpenCV or in-house made algorithms for doing those kind of things related to preprocessing. What we have is, first of all, we have the most powerful and the most accelerated OpenCV library for Intel as part of OpenVINO. But then we also have, if you are limited to those kind of basic options, then we have those preprocessing things as part of OpenVINO API. So we automatically identify the size that you want to resize to based on the input blobs and the network format and the network that you expect. We also identify which format you want to convert, and we do the conversion. And since it happens in the same framework as we do the inference, then you actually have significantly less conflicts between those. And that we guarantee you that this is the best acceleration that you can get out of the resize versus inference and things like that. So there is a lot of benefits using this built-in mechanism, because you don't have things conflicting. You get the fastest acceleration. But then let's just look again on the same pipeline. Quite frequently, we also have discussions about how much FPS certain platform provides. We have measurements on the inference, how many FPS certain things can provide. But again, going back to this pipeline, the inference is just one component. Yes, it is extremely resource hungry, but other components are also consuming like CPU and maybe other resources, but not only consuming, they conflicting with the inference as well. So if you wrote your pipeline incorrectly, or if the framework that you're using is not counting for other components running, then basically what you have is you sort of have a significantly degraded performance. So starting with OpenVINO R1 this year, we have switched OpenVINO from OpenMP to TBB. And the reasoning was exactly that OpenVINO with the TBB actually capable of working with other components that are running on the system without major conflicts. With the OpenMP, you get very good benchmarking numbers. As you can see, we degraded benchmarking numbers for 3%, 1 to 3% for pure inference, but we get up to 70% optimizations when we are measuring the actual pipelines, when we are measuring the actual applications that are doing similar tasks. Not necessarily this, but other tasks as well, like multiple networks, 4 to 5 networks doing like a tandem of the work. So what I'm trying to say is that pure inference numbers doesn't necessarily mean that the system or like software solution or hardware solution fits your needs. You need to look at the whole pipeline that you would be running. Then one of the things that we frequently see is that certain networks are not matching certain hardware. Yes, that is true, because most of the deployments are actually in conflict with the academia frameworks, with the academia results. So let's look here. We have a list of the networks from 1 to 12. Those are networks that are like competition winners, right? They're like image recognition, object detection winners. There is a segmentation, like DSSD at some point was extremely popular because it was providing significantly higher object detection results, right? But then let's look at the graph. We have a number of parameters versus gigaflops. So as you can see, we have quite a lot of networks that are very high on this graph, very high to the right, like 256 million of parameters versus like what, 512 gigaflops. So this kind of network is solving academia task. Like it's doing the object detection very good, perhaps 1.1% better than previous one, but it's not suitable for deployment. If we look lower than a little bit, from 13 to 17, those are networks that are providing significantly higher results. Like if you look at the right column, those are FPS numbers on i7. As you can see, the number is like significantly higher. Those networks doing the same task. Yes, they are not as accurate, perhaps few percent lower, but you get significantly higher throughput with those networks. So what we recommend is those are actually within this box, the gray box that I shown here. So what we recommend is that before you actually go for a deployment and you select the network from academia results or something like that, what we recommend is that there should be some investigation done prior to this to understand if this network actually fits the deployment scenario, if this network is so deployment friendly as you want, because you get a super fast execution with minimal degradation of the accuracy. So to prove that, we have, as part of OpenVINO, we have Open Model Zoo, which is a set of networks that we specifically pre-trained for certain tasks. So for example, we have face processing networks, we have vehicle detection networks, we have quite a lot. As you can see, we even have a body pose detection network as an example. We have semantic segmentation, things like that. So those networks are extremely lightweight, but at the same time, they provide same accuracy as close to the same accuracy as academia networks. We sort of provide them free of charge. You can use them as an example. We also have them integrated into the demos that we have, right? So we have demo applications that are using exactly those networks. We built this demo application in a way that we showcase how best to build a pipeline, exactly what we talked about previously. We build them in a way that you have to be efficient as possible on a pipeline level, not on just an inference. We use those networks, like for example, demo on the left, I think uses at least 3 or 4 networks in parallel. This is a face detection, then head pose detection, which detects the angle for the head, detects the age and gender of the person, and things like that. We have a body pose, and we have on the right, we have a demo with vehicle detection, license plate recognition, and I think it's also does vehicle color understanding and things like that. So what we recommend you to do is that go and just check what's available there. Those networks are free of charge. You can use them. You can also use them as an example. We provide model templates for those. So you can take your data set, you can take the model template for one of the public networks that we have, for one of the networks that are highly efficient, and you can train them on your data. You can train them and get them up to speed with the OpenVINO. Right. So and then also look at the samples that we have, because we sort of trying to solve typical use cases that exist, and we sort of trying to showcase how to do that efficiently. So it's a pretty big piece of the distribution that we have, because we are trying to come up with the solution that's so easy to take and start use out of the box. Like for a popular task like face detection, you can just take the network as that exists there and get like 300 FPS or something like that. So as a conclusion, few things I want to say. So switching to OpenVINO is easy, first of all, but then it gives you additional performance, additional throughput, and things like that, right? So ensure that you use additional features. Look at the samples, the features that I was describing. Look at the samples, look at the code. There are way more things than just plain inference. And then we have a very good offering of the models, pre-trained models on our own proprietary even data sets, as well as we recommend you to look at not just inference numbers, but on the overall pipeline. So I think I'm done.
Good job.
I'll draw your attention to the microphones in the center aisle here for any questions. I will start with one.
Okay.
I'm going to step back a little bit because there was a lot of implementation specifics in your presentation. Yeah. The whole idea of the OpenVINO Toolkit has always been intriguing to me. The ability to write an application that will run seamlessly on one or a variety of simultaneous heterogeneous architectures. And you come from a company that's got CPUs, GPUs, right, both integrated and rumored standalone again soon, FPGAs, a variety of dedicated accelerators. So I assume that's functional compatibility, obviously not necessarily performance compatibility, otherwise there would be no need for an accelerator. Yeah. But can you talk about that, both migrating from one compute platform to another, implementing on a platform that has multiple simultaneous heterogeneous processors, and then how the overall flow kind of goes from one to the other.
Yeah, that's a very good question. So there was an indication that you have compatibility across the platforms. So typically, one of the scenarios, or actually one of the basic scenarios that we recommend to the customers is that you start first with the CPU. You create your application, you run on CPU, you ensure that it is functionally compatible. You do the debugging, you do the all of those, you're cutting corners basically there, because CPUs are extremely easy to develop on. It's you have a lot of tools comparing to accelerators and things like that. And then if you feel that, okay, my application is working, my pipeline is working, perhaps not as highly performant as it is, you can switch to accelerator by changing literally close to one line in the code. And the results are the same. The code structure is the same, so it's extremely convenient to start with the CPU and ensure that compatibility on a functional level helps you.
And now you all know why Intel bought ITSEs a few years ago.
Yeah.
All right, questions from the audience?
I have just a couple of questions. Thank you for the talk. Very interesting. First question about the TensorFlow comparison you made. You made the comparison with the full-scale TensorFlow, not TensorFlow Lite. Is that correct?
Yes, but TensorFlow Lite on CPU is kind of a non-existing thing just yet. So.
Right, but the performance 2x is against the TensorFlow, full TensorFlow implementation.
So, but it is accelerated by Intel, so we tried to do as much as possible accelerations there. So to tell this story, perhaps for the last year, it was 5 times accelerated or even more. So, and yet there are some things remaining that we can achieve for pure inference scenario.
Right. And the OpenVINO APIs and the toolkit as a whole, it supports only Intel products, is that correct? It doesn't support, say, third parties, GPUs or TPUs?
Yeah, right now that's the case, but since it is open source, we sort of were welcoming others to contribute. Since it has a plugin structure, you can essentially bring your hardware, write plugin. We will gladly accept this as a contribution. There is no problem with this. We never were limiting this to being specifically Intel.
Are you working right now or planning to work with other people, third parties who develop their own GPUs to make sure that they're compatible with OpenVINO APIs?
Yeah, so let's put it like that. There are not all the things that we can talk about, but let's say that we are welcoming people to work with us. We gladly help them.
Thank you so much.
Yeah.
Is it quick? All right.
Very quick question. There were 2 things that caught my attention. One of them, you talked about heterogeneous architectures, and second, you were talking about multi-threading and parallelism.
Yeah.
Are you implying that with an OpenVINO, you can take a model, partition it, run it on 5 cores, 2 of them could be Intel, 2 of them could be FPGAs, and 1 could be a GPU?
Exactly, that's what's happening. So basically, when you go and start running network on FPGA, for FPGA, not all the layers can be implemented efficiently. So what we do is that we automatically split the network into parts. And some parts are running on FPGA, some parts running on CPU. We switch the data automatically. You won't even see this. So basically, that's what's happening.
Okay. All right. And you're sticking around for a while in case there's other questions? Okay. Come find them if you have more.
Yeah.
Thank you very much.
Thank you.
Yeah.